So my name is Anand. I'm a faculty member here. This is Sarka. He is the one who's been sending all of you emails. This is Naman. He's also been, and who else? Parag is here. There's Parag. Ritabruto.
Ritabruto was at the desk.
Yeah, he's the one at the desk. So these are the 4 students who've been helping us put all of this together. And yeah, and all of this definitely would not have been possible without the support from the Walmart Center for Tech Excellence. So they've been funding this event, so a big thank you to them. And yeah, so yes. Yeah, so we have a terrific lineup of speakers, Professor Prajakta Namborkar, Professor Neeldhara Mishra, Professor Akash Kumar who's here, Professor Naveen Garg, Professor Amit Kumar. They are some of the best in this business in India, and it's a great opportunity for you to be getting to learn about approximation algorithms from the best people in India. Right, so in case you're wondering what is approximation algorithms, I'm sure some of you are wondering what is that. Please let me call upon the first speaker for the day, Professor Prajakta Namborkar. She's a faculty member at the Chennai Mathematical Institute. She's been doing a lot of amazing work on approximation algorithms. And yeah, so she'll be starting us off, telling us about approximation algorithms and what it means and a lot more. Prajakta, please. Yes, yes.
So, how much of the code I can use?
The whole code is there. I can't see beyond.
No, you can't see it, but you can see on the recording.
Let's mark that one. Very good. And this is what
Good. You can see it in the other complete.
I think these work.
To here, it's visible.
Yeah.
I can also have, I have to also leave out a lot of top portions. So, I would like to thank the organizers who have done it. So, I would like to thank the organizers for inviting me here and giving me the opportunity to do the opening session. I hope I will do justice to it and not scare you off or bore you. And then, anyway, you should try out the rest of the sessions even if you feel it's quite boring or not accessible. Alright, so let's start from the beginning. Can everybody read this? Okay, I'll write one bigger. I think you can also think of moving forward because there are lots of empty places. Suppose this is a bit okay? Yeah, so we will be dealing with discrete optimization problems. So what are these problems? There is the input is a finite set or some object. For example, a graph or a set. Typically the solution set is large. And our goal is to find a solution of minimum cost or maximum value. There are several possible solutions, but we want one with minimum cost or maximum value. So if we want to find a solution of minimum cost, we consider it as a minimization problem. And these type of problems are called as maximization problems. And such a solution which either minimizes cost or maximizes value is called an optimal solution. So this is a term we will use here onwards, optimal solution. And of course, we have limitations on how much time we can spend. So we want to find such a solution in polynomial time. So polynomial time algorithms are practical in all respects, whereas exponential time algorithms are not practical on large instances. So this will be our focus, to get a polynomial time algorithm. Now as it turns out, many discrete optimization problems of interest are NP hard, and so many such problems are NP hard. So we have no polynomial time algorithm unless P equals NP. And we don't believe that P equals NP, so we don't have hopes for finding polynomial time algorithm to get an exact or optimal solution for such problems. Somewhere we have to compromise, and one way to compromise is about this optimality of the solution. So when we design an algorithm, we will not ask for an optimal solution, but we will settle with a solution which is not too bad as compared to the optimal one. And this is again a very practical thing to do. For example, instead of paying say 10,000 rupees, you wouldn't mind paying say 10,005 rupees if the solution comes to you really quickly without spending too much of time. Right? So we will compromise on the quality of the solution, and what we will do is find a suboptimal solution which is not too bad compared to the optimal one, or which is close to optimal. Please stop me and ask questions if I am not making things clear. So this is how the approximation will be. It will be in terms of the solution cost or value. So let me write a formal definition now. So an algorithm is an alpha approximation algorithm for a problem. Whenever I say problem, it will be this discrete optimization problem. If for any instance the algorithm finds a solution which is within alpha factor of the optimal one. And for a maximization problem, alpha will be smaller than 1, whereas for a minimization problem, alpha will be larger than 1. Okay, any questions so far? And of course, we don't want to spend too much time, that is what we started with. So, this algorithm should run in polynomial time. So, I will not spend too much time now on this abstract setup. I think it's more or less clear to everyone, and it will be clearer through an example. So, let me start with our first discrete optimization problem. We will see the vertex cover problem. Let me define what the problem is. So, we are given a graph. A subset of V is a vertex cover of G. If each edge has at least one endpoint in S. For example, if this is the graph, then we want to pick a set of vertices, a subset of vertices, so that every edge has at least one endpoint in that set. So here, for example, we have to pick some vertices. So this is not a cover because this edge doesn't have an endpoint, and so on. I suppose the circle vertices form a vertex cover. Of course, we can pick the whole vertex set, and that is trivially a vertex cover, which is not so interesting. So our goal is to find a smallest or minimum size set of this kind. So goal is minimum size set S. So any thoughts, questions? Sorry? Yeah. Alright, so one thing that we can now we want to design, this problem turns out to be NP hard. It's a very simple looking problem, but nevertheless it's NP hard to find a minimum size set of this kind or minimum size vertex cover. So we want to find an approximation algorithm. So our typical recipe to design an approximation algorithm will be like this. So one is of course design an algorithm, and it should be a polytime algorithm. So design a polytime algorithm. We have to show that this algorithm indeed computes a valid solution. For example, it should not output a set which doesn't cover all the edges. And the solution size is within alpha times optimal for some alpha. Now, the first question that comes to mind is, if the whole problem lies in the, or whole difficulty lies in the fact that we don't know how to find the optimal value. How do we show that the solution size is within some factor of the optimal without actually knowing the optimal? Right? So, what we will be doing is, we will find some bound on the size or value of the optimal solution and show that our solution is within alpha factor of that. So, for vertex cover, we will make one observation before we actually design an algorithm. So, let's observe something. So, if two edges E1, E2 don't share an endpoint, or don't have a common vertex, then of course they cannot be covered by the same vertex. An edge is said to be covered if it's one of its endpoints is present in S. So if we have two edges like this, E1 here and E2 here, then of course for this edge we have to pick an endpoint. For this edge also we have to pick an endpoint distinct from what we did for E1. And the simple observation tells us that if we have k edges of this kind which do not share an endpoint, then that tells us that all these k edges need at least all these k edges require that we have at least k vertices in our solution. So if there are k edges which are pairwise disjoint, or they don't have any pair of them doesn't have a common vertex, then even optimal vertex cover has to be of size at least k. So, what did we say? If the graph has k many disjoint edges, then we need at least k vertices in our vertex cover. No set of vertices with size smaller than k can be a vertex cover, because k distinct vertices are required to cover these k edges. So this suggests us an algorithm. Let's write this algorithm and see how it performs. So just pick an edge in the graph. We know that for this edge, either u should be in our solution or v should be in our solution. So let's start with an empty set, which is clearly not a valid solution. Now when we pick an edge, we know that one of them has to be included in S. Let's play safe and include both of them. Okay, so the picture looks like this. We have this edge in graph. There is U, there is V. They have some other edges also incident on them. Now once we include u and v in our cover, all these edges are covered. They already have one endpoint in S. So we don't have to worry about all these set of edges which have either u or v as one of their endpoints. So let's delete all of them. So in fact, let's delete u and v from the graph. All these edges which are incident on u or v will get deleted. And also their incident edges which will automatically get deleted. So sure, we have covered E and we have covered the edges which were incident on UV. We still have possibly lots of vertices and edges left, which are clearly, the edges are clearly not yet covered. So there are some other edges here, they are not yet covered. So we will repeat this procedure. And how long should we repeat? So clearly we have lost 2 vertices from G, so now we have a smaller graph. We will continue like this and eventually the graph will become empty. So we will do this as long as G is not empty. And now we want to output or return the set S. Looks like we have not done a good job, right? I mean, why did we include both vertices when we could do with one? As it turns out, if we just take one, we really don't know which one. And if we make a bad choice, we might pay a price later. So here we have kind of played safe and included both so that, well, instead of one, we are including 2 vertices. One might expect that this will give 2 approximation because of this. And it indeed does, and we will show that. Maybe let's execute this on a small graph. Okay, we pick an edge. So let's say we pick this edge, include both its endpoints in the set S. And when we delete these, lots of things will get deleted. So the undeleted ones I will mark. So once we include these 2, we will have these leftovers. Right? The red ones are the leftover ones after we delete these 2 vertices. Now we will repeat the same procedure. So pick another edge. Let's say we pick this.
Should we do this process until G is empty, or it can be like we have isolated vertex and we stop?
So if the original graph, sure. I mean, we don't worry about isolated vertices because our edges are all, our goal is to cover the edges. So we want one endpoint of an edge to be in the set S. So if a vertex is isolated, it is not going to contribute towards covering any edge. So they cannot be part of our solution, we can ignore them. So sure, I can say that until the edge set is empty. Okay, so we pick this edge, include both its endpoints in the cover, and even delete those 2 vertices. I am not erasing it because it's difficult to erase and retain the rest of the graph. So I am just marking the undeleted ones. So I suppose these are the ones which are not deleted. So now suppose we pick this edge again and include both its endpoints. Now everything will get deleted as someone pointed out, this vertex will remain as an isolated vertex. Fine. And even this example shows that we have not done the best possible. But nevertheless, so we are looking for an approximation algorithm, and let's actually give a proof that this gives us a reasonable approximation.
So you write here that G equal to 5 means
I can write E equal to 5.
Yeah.
This is better because we might have isolated vertices, which we don't care. Erase the definition now. I hope everybody remembers what a vertex cover is. Now, the first thing to show, or the first thing we should be concerned about is, we are outputting this set is it at least a vertex cover? Because if it is not even a vertex cover, then we are outputting an invalid solution, which is not what we should be doing. So first thing that we should prove is, the set S output by the algorithm is a vertex cover. Is it obvious? It is, right? So why is it obvious? Say it again. Yes. So in particular, one simple observation here is that when does an edge get deleted? An edge gets deleted only if at least one of its endpoints gets included in G. In S. If we want to prove this, we should write the observation that an edge gets deleted if and only if it gets covered. So in particular, if some edge xy is not covered, by our solution S, then we know that x is not in S and y is also not in S. But then how did this edge get deleted? Certainly x and y were not deleted. Only the vertices which we include in S get deleted. So here, because that edge is not covered and these vertices are not in S, E must still be present in G, and hence G or the edge set will not be empty. So this contradicts our termination condition that our edge set is empty. So what we have constructed is at least a valid vertex cover. Now we have to prove that it is a true approximation to the optimal vertex cover. Delete the algorithm. So now we want to prove our main result, that is size of S is less than or equal to 2 times size of optimal vertex cover. So that is where this observation which we made initially will come handy. So clearly the edges that we have picked in the by the while loop of our algorithm, those edges do not have a common endpoint because we picked even, we included both its endpoints in the cover and deleted this edge as well as its endpoints. So the edge that is picked later cannot share an endpoint with even. So if our algorithm runs for some k iterations, clearly the edges that it has picked in each of these iterations, they do not have a common endpoint. So let the algorithm runs for some k iterations. And pick edges E1 to Ek in iterations 1 to k respectively. Now we observe that Ei and Ej have no common endpoint. Whenever I is not equal to j. So no two edges that the algorithm picks have a common endpoint. And hence, as we observed earlier, even the optimum solution has to include at least k vertices in the cover. So size of optimal vertex cover has to be more than equal to k. What is the size of our solution? 2k, because if in each iteration we pick an edge and include both its endpoints in the cover. So in these k iterations we would include both endpoints of E1 up to Ek. So size of S is exactly 2k, which is less than or equal to 2 times the size of optimal vertex cover.
I have a,
Yeah, sure.
so, why is my optimal vertex cover size always greater than or equal to k? It's greater than or equal to k, it's equal to k in the case where my edges are disjoint, but suppose in a star kind of a graph, so my,
In a star, how many disjoint edges can you find?
so my,
This kind of graph, right?
right, so here my optimal vertex cover is of size 1.
Yes. And what will our algorithm do? It will pick any one edge, include both its endpoints. So it will include, say, pick this edge, include this one and this one, and delete these two vertices.
Okay, but I was confused about the definition of k because in the observation there, there are like k edges in total, but here my total number of edges is not k, but
Here also we said there are k edges which are pairwise disjoint.
alright.
So if our graph has k many pairwise disjoint edges, then we need at least k vertices to cover them.
Right, so
Right? Because whatever in endpoint of E1 we include, it cannot cover E2 to Ek. Right? So in a star kind of graph, what will happen is precisely this vertex and this one will get included, and the whole graph will become empty. So instead of one single vertex in the cover, you will have two.
right, got it. So basically we mean the number of pairwise disjoint edges, like
Yes,
not
there are
just k.
k pairwise disjoint edges.
Excuse me, I was thinking of an algorithm. What if at each iteration we take the vertex with maximum degree, and then we delete that vertex and continue that process?
Yeah, so this is the most natural greedy approach that would first come to mind.
Yeah.
So I will not talk about it here because it is present in the problem set, and there you will figure out that it is much worse than a 2 approximation. So you will be given time to think about it. Now you can think from now until the problem session, but it will give something much worse than 2.
Actually, considering similar idea, when you wrote the algorithm, it doesn't matter like how you pick the edges, you still get 2.
Yes.
So no matter like if you pick the maximum degree or anything, so is it like 2 the best thing that you could do, or you could go below 2?
Under standard assumptions that we believe, 2 is the best possible.
Okay.
There is, 2 is the best possible constant here. No other smaller constant is possible if we believe the assumptions or conjectures. So yes, it is a very simple algorithm. It looks like it doesn't care how the graph is, what the degrees are, and so on and so forth. But yeah, this is indeed the best that we can do.
How do we prove that 2 is the best we can do?
That is a bit tricky to prove. So we can't prove it here. You can see that the algorithm doesn't do better. We can't analyze it in a better way from this example. That the optimal is 1, but our algorithm will give 2. So that way, the tightness of our algorithm, or the tightness of this approximation factor 2 for this particular algorithm comes from this example. Okay, that we cannot just do a better analysis of this algorithm and get a better approximation factor, because here this is an example where our algorithm will actually give 2 times optimal. But in general, proving that no algorithm can do better than 2, give a better constant approximation than 2, that takes a lot more work. I think in the last session you will have some idea about showing inapproximability, maybe not this particular one, but there will be something about that.
What about applying BFS from an arbitrary node and adding to vertex cover every odd level? That also an option, and will that be better than 2 or worse than 2? Any way to prove it?
So, better than 2 is difficult to prove because, as I said, under some plausible conjectures, we cannot get a better constant than 2. But yeah, you can try to analyze it and either see that it gives much worse, or you can try to construct an example where either it will give worse, or otherwise one has to prove that it will give a 2 approximation. So that is also another thing to try out.
More questions? So please use the mic when you're asking questions. That will then be on the live stream.
Yes, and those who are watching online will also know what question is being asked.
Yeah.
Anything else? Is everybody convinced that this simple looking algorithm, very naive algorithm, is giving us a 2 approximation? Okay, so this is about vertex cover. There are some generalizations of this. For example, here we are treating all vertices as equal. So what if there are costs on vertices? So when you include a vertex in S, you have to pay certain cost. And then instead of size, you want to minimize the cost. As it turns out, one can also get a 2 approximation there. Not by this algorithm, but by a more sophisticated algorithm. So again, I will not be covering that. But I will be moving to another problem after this. But let me mention this generalization here. So the generalization is vertices have non-negative costs. find a minimum cost vertex. Clearly, this algorithm will do much worse. For example, if we pick this edge first and this vertex has cost 1000 and others have 1, then this will be arbitrarily worse than the optimal cost. So we cannot use this algorithm. Find a minimum cost vertex. Let me also put one more remark. So we said that the problem is NP hard, and here we give a 2 approximation. For bipartite graphs, the problem can be solved optimally in polynomial time, and in fact, if you know what matchings are, then size of maximum matching turns out to be the size of minimum vertex cover. So nevertheless, I will not get into that either at this point, but you are welcome to think about it and figure out if you have not seen it earlier. There is a polytime algorithm to get an optimal vertex cover. I will write VC for vertex cover in bipartite graphs. So, since we have limited time, we cannot dwell into everything here, but these are the pointers which you can explore offline, and if you have any difficulties in any of these things, you are welcome to catch me, or in fact catch any of the speakers or the TAs or anybody. Okay, so here we will stop with vertex cover and we will go to another problem. So let me erase all this. So the second problem that we are going to consider is the maximum cut problem. So what do we want to do? Again, we have a graph which is undirected. And the problem is to find a partition of B, or the vertex set, into two parts. A and B should be just V minus A, so every vertex goes into one of the parts. Such that number of edges with endpoints in different parts is maximized. Okay, so here a cut is a set of edges such that there are only two parts, right? And the edge has only two endpoints. So E has one endpoint in each part. And of course the goal is find A and T so that size of the cut is maximum. So the earlier one was a minimization problem, now we are seeing a maximization problem. So you can imagine that the edges represent some sort of conflicts and we want to separate out the vertices so that the conflicts are minimized, or most of the conflicts get resolved. For vertex cover, I told you, although I did not prove and left it to the problem set, that a greedy approach where a vertex with maximum degree is included in the cover and so on actually doesn't do very well. Here, as it turns out, a greedy approach will do fairly well, and that is what we will explore now. So there are several algorithms which are very simple. All of them give two approximation. Now here, well, not two, but I should say half approximation. So I think I have time for maybe two of them. I'll cover two algorithms here. So let's first cover a randomized algorithm. So we don't know which vertex to put into which parts, right? So you will see some randomized algorithms later in one of the sessions today. So let me start with a simple one here. So again, we have our vertex set V. We have these sets A and B. Let's start with empty sets. So start with both A and B being empty. Clearly this is not a valid solution because we want every vertex to be in one of the two sets. Now we want to take a vertex and put it in either A or B. How do we do that? We just toss a coin. If it comes heads, we will put it in A. If it comes tails, we will put it in B. So first vertex, of course, we can just start with putting in A. So let's say V is V1 to Vn. There are n vertices. So now just put V1 in A. Doesn't matter if you put in B or toss a coin for V1 as well. Then let's toss a coin for it.
Can there be edges within the part?
There have to be, right? For example, if this is your graph, that is a good question. So let's figure this out. So these are three vertices. Now clearly two are going to be in one part, one is going to be in the other part, because we are not allowed to have one part as empty, otherwise we would have put all of them here, but we don't want to do that. And of course that also doesn't give us a good cut, because it will be a zero size cut. So we will put two vertices in one part. Let me denote it with square, one in the other part which will denote with circle. So this goes into A, this goes into A, this goes into B. This is without loss of generality. So there will be edges between two vertices in A. So there are three edges here. We cannot get a cut with all three edges in it, because then we will have to make three different parts, but we are asked to make only two parts. Otherwise we would have just made n parts and cut all the edges. Okay, so yeah, there will be edges between vertices in A, there will be edges between vertices in B, and we can't help it. So here the maximum cut is going to be of size 2, we can't get 3. So toss an unbiased coin. If outcome is H, put Vi in A, else put Vi in B. And since we are doing this for every vertex, what will happen at the end of this for loop? Every vertex will end up either in A or B. So at least the requirement will be fulfilled that we will have a partition of vertices into two parts. Here we will return A and B. So one observation is that the sets A and B indeed partition B. So we don't violate the first requirement. And this is irrespective of what the outcome of the coin toss is. There is some small chance, in fact a 1 over 2 to the n chance that everything will land up in A. There is also a 1 over 2 to the n chance that everything will land up in B. But then again that chance is very less, just 1 over 2 to the n. But it looks like we may turn out to be unlucky and we may not do very well. So how do we analyze such an algorithm? So the algorithm is randomized, we will also analyze it using random variables. So first of all, what is the probability that a particular edge will be cut, or it will have its endpoints in different parts? So what is the probability that a particular edge let's say E equal to UV is cut? Say it again. 1 by 2, right? Because there are 4 possibilities. So there are 4 possibilities, either UV both are in A, U is in A and V is in B, U is in B and V is in A, and both are in B. So each have probability 1 by 4. Because U goes in A with probability half, independent of that V goes in B with probability half, so on and so forth. So each of these outcomes are equally likely, each have probability 1 by 4. These are the ones which correspond to E being cut. And the probability is clearly half. probability that E belongs to the cut is exactly half. So this tells us that the expected number of edges which get cut will be roughly half the total number of edges. Now how large can the maximum cut be? At most it can end up cutting all the edges. So if at all it is possible, the best cut would be to get all the edges in the cut. This example shows that it may not be possible, but nevertheless total number of edges is an upper bound on the size of the maximum cut that we can get. This says that we can expect to get half the edges in our cut. So we will get a half approximation. Let's make it formal now. But this is the rough idea. So let's analyze this properly. So define random variables xe for each edge in E. And they take 0, 1 value, so xe is 1 if E belongs to the cut or E is cut, and it's 0 if E doesn't belong to the cut. So these are 0, 1 random variables that we are defining. And again, probability that xe equal to 1 is half, which is also the probability that xe equals 0. What is the size of the cut in terms of these variables xe? Just sum of these xe, right? Because those edges which are in the cut will precisely have xe equal to 1. So summing over all x's will give us precisely the size of the cut, because those edges which don't belong to the cut will only contribute 0 to the sum. So size of the cut is sum over all edges, random values of the random variables x. This is all randomized, and depending on the outcomes of our coin tosses, the values of x will vary. Or we execute the algorithm once, we will have one outcome. We execute it another time, we will have another outcome, and so on. So we are considering one run of the algorithm and considers what happens in that particular run. So the size of the cut is just sum of these random variables. So now let's see what is the expectation of this size of the cut. Now expectation has a nice property that, okay, let me write expectation on both sides. Now expectation has a nice property that we can interchange this expectation and summation. This is called linearity of expectation. It does not need independence of these random variables x. As you see here, they are not independent. For example, if we know that these two edges are in the cut, it determines that this edge cannot be in the cut. So these x's are not independent. Nevertheless, we can still apply linearity of expectation because it doesn't need independence. So I take out the summation and put the expectation inside. What is the expected value of xe now? Half. So 1 times half plus 0 times half, which is nothing but half. So expectation of xe is 1 into half plus 0 into half, value times the probability, which is just sum over all edges of the value half, and there are mod e many edges, so this will be mod e over 2. Does it? Yes, there is some question.
So this algorithm says that we'll get a cut of size m by 2 with high probability.
Yes, so if you call m to be the number of edges, sure. I am not saying with high probability, I am saying in expectation.
Yeah, and can it happen that actual maximum cut is less than m by 2?
No, so that is the fact, right? As in, it cannot, so this says that the expected size of the cut is mod e over 2 or number of edges over 2, which means there must be a cut in the graph with at least these many edges.
Okay, so the cut get by this algorithm will be smaller size of actual max cut always.
Yes, actual max cut may contain all the edges, for example, this has mod e over 2. But since actual max cut can have size at most mod e, this tells us that we are giving a half approximation in expectation. So let me write this down. So the algorithm outputs a cut that is a half approximation to the max. So of course size of max cut is less than equal to mod e. And of course this is not deterministic, this is in expectation. Expected value of the size of the cut is mod e over 2, which is more than equal to half the size of the max cut. Okay, so we are not guaranteed that a particular run will be successful, we will get a cut at all and so on. But this is what we can hope in expectation. We have a half approximation in expectation because we are using a randomized algorithm. And as someone pointed out, this also tells us because this is the expectation. Expectation is nothing but taking an average over all possible ones with the corresponding probabilities, so weighted average. So since this is sort of weighted average of all possible outcomes, there should be one cut which actually achieves this expectation. If you take an average of several quantities and it turns out to be some number x, then every quantity cannot be smaller than x. That is the averaging argument. So since this expectation, which is a weighted average, weighted by probabilities, is this much, there has to be one cut which contains at least these many edges. Every graph G has a cut-off size more than equal to mod u. I have like 20. Oh. Is it clear so far? If you have not seen randomized algorithm before, it might sound a bit mysterious. But I suppose you have seen probabilities and expectations. So the calculation should not seem very alien to you. Yeah, maybe if you have seen probability as a separate subject, here is where probability helps us in designing and analyzing an algorithm. So, nevertheless, if you are not very happy with having a randomized algorithm where our whole fate depends on the outcomes of coin tosses, we will also go for a deterministic one.
If we were to change this optimization problem to the corresponding decision problem and use this algorithm, would the error be bounded on both sides, or would it be a Monte Carlo or a Las Vegas type of algorithm?
So, you want to determine if there is a cutoff certain size. What do you mean?
Yeah. So the decision problem would be you pass it a integer that tells you if there's a cutoff that size.
Yeah, so here I have not quite computed the variance and so on. So I am not sure how concentrated the outcome is around the expectation. But particularly we won't do that because we even have a deterministic algorithm. So rather than analyzing what is the probability that we will get a cut of this size or close to this size, that would be the next thing if we did not have a deterministic algorithm at all. But since we have a deterministic one where we can actually get a cut of this much size, we will focus on that right now. Sorry? Because we don't need the probabilities anymore. So yeah, let's go for a deterministic algorithm. So what were we doing so far? We just started with two empty sets A and B, and we took vertices one by one, tossed a coin and put them into A and B, A or B accordingly, depending on the outcome of the coin toss. Let's do it a bit wisely, why not? So let's put the first vertex in A deterministically. Doesn't matter where we start. Now for every subsequent vertex, we can check whether it has more edges to vertices in A or more edges to vertices in B. So start with V1 in A and B to be empty. So if Vi has, or let me write that, that's okay. If Vi has more neighbors in A than in B, Where should we put Vi? We should put it in B so that more edges will end up in the cut. It has more neighbors in vertex Vi, which is under consideration now. If it has more neighbors in A as compared to neighbors in B, it makes sense to put Vi here so that these more edges will end up in the cut rather than these fewer edges. So include Vi in B. If that is not the case, include Vi in A. So similar to the coin toss, but instead of tossing a coin, we are now making a wise decision depending on where the vertex has more neighbors and where it has fewer neighbors. If it has equal number of neighbors in both, then it will end up in A because of the way it is written. Now, looks good as in at every time we are making a wise choice or whatever, a greedy choice in some sense. How do we analyze this again? Yeah.
We look at it edge-wise. So every edge gets analyzed in some sort of. So we look at it edge-wise. I think I haven't thought about the entire thing, so I'm just saying my idea. So we look at it edge-wise. What I guess is that when we analyze it, so every edge will be analyzed once, and in every step there will be some edges that we will analyze, and we will always make sure that in each step we put more edges in the cut than out of it. And in this way, if we analyze all the edges, we will end up with greater than or equal to E by 2 edges in the cut.
Yes, so that is the hope. Of course, there will be lots of edges this Vi has where the vertices are not yet considered. Right? So we don't know what is going to happen to these edges. All we know is that, yeah, so all we know is that these edges will land up in our cut if Vi goes to B. And for these edges, the decision will be made later on it, depending on where their other endpoint goes.
That's a question. So I think that throughout the whole algorithm, you every edge once, and in each step you basically invariant that the edge already visited, only more than half of this is already a cut. This is the invariant we are maintaining.
Yes, so in some sense, for those edges, so every time we decide to include a vertex into A or B, the fate of some edges gets decided. So here Vi is in picture. Depending on whether we put it in B or depending on whether we put it in A, the fate of all these edges will get decided. Either these edges will end up in the cut or these edges will end up in the cut. So which vertex decides the fate of an edge? It's not the first endpoint, it's the second endpoint that we consider. Right? So we put these endpoints of these edges already in A. These edges have already their endpoint in B. But whether they are in the cut or not gets decided when we decide to put Vi in A or B, which is their second endpoint. So let's write this as an observation because it's so. Fate of an edge is decided by its second endpoint. What is first and second? The order in which we are considering them. So this is an informal statement, but I hope it makes sense to everybody. We are considering vertices in certain order. For an edge, whenever its first endpoint gets considered in this order and it goes to one of the two sets, nothing is clear about that edge. Just like for these edges, it's not clear whether which one are going to land up in the cut. Only when Vi gets put into one of these two parts, we will know which edges land up in the cut and which edges are not in the cut. So the deciding vertex for an edge is its second endpoint. So for each vertex, denote by RV the number of edges which have V as their second endpoint. In particular, for every vertex V, RV denotes the number of edges whose fate was decided by V. Are these two statements making sense to everybody? So for every edge, some endpoint is going to be first and some endpoint is going to be second. So every edge will be counted into this number, and it will be counted only once. I mean, an edge cannot have two endpoints deciding its fate. One of them is going to be the first one, which will not be a deciding factor at all. The second one will be a deciding one. And by fate again, I mean whether the edge ends up in a cut or not. So for example, for this vertex Vi, which edges will contribute towards the number that RVI? Only these edges will contribute. So number of these edges is precisely the number RVI, because Vi is the second endpoint for all these edges. So each edge is counted exactly once. This quantity. So what is this quantity? Okay, each vertex is responsible or let's use the word responsible or deciding for certain number of edges. That is RV many edges. Now, on the other hand, for every edge there is one endpoint which is the second one which will decide its fate. So if we look at this quantity summation over V RV, what should this quantity be?
It will be greater than equal to max plus equal to E.
This will be just number of edges. Why? Because whether an edge lands up in the cut or not, it will be counted in this number RV. So I am not saying that RV is the number of edges which end up in the cut. RV is the number of edges whose fate or whose fate is decided by that particular vertex V. So here, if you put Vi in A or Vi in B, irrespective of that, all these edges will have Vi as a vertex responsible or deciding for them, and all these edges, the number of these edges will contribute to RVI. Not all of them will be cut. Either this set will be cut or this set will be cut. But the whole number will be RVI. If Vi goes to B, for example, these edges will not end up in the cut, but nevertheless they are contributing to this number. Similarly, these edges will end up in the cut, they are also contributing to this number. So since every edge has a second endpoint and the number RV is counted, every such edge counts towards this count RV. So this is going to be equal to just the number of edges. Now what can we say about our decision of putting Vi in A or B in terms of this count? So in particular, when we choose to put Vi in A or B depending on the number of neighbors it has in A or B, how many of these RVI edges are going to be in the cut?
RVI by 2.
Yes, so since total is RVI, either it has at least half the neighbors here or at least half the neighbors here. So since we are putting Vi into that set where it has fewer neighbors, at least half of these edges will land up in the cut. So at iteration I, at least RVI by 2 edges get into the cut. Can they change later? Can it happen that now when we put Vi here, these edges land up in our cut because they have one endpoint already in A and then another endpoint Vi that goes to B. Can this situation change later?
No, because it's a second one.
It's the second vertex, right? So we are never shuffling vertices once we put them in A or B. We are never saying that move a vertex from A to B or B to A. So once both endpoints of an edge goes, both endpoints of an edge go either into A or B or in one in A and one in B, it is frozen. The status of that edge cannot change later on. So once we decide to put the second endpoint of an edge to one of these two parts, either that edge belongs to the cut or it doesn't belong to the cut. That doesn't change later on. And since we are acting greedily, Vi is the second endpoint of these RVI many edges, whose first endpoint is already in one of the two parts. So since we are acting greedily, at least one of the Vi has at least half of these RVI many neighbors into either A or B, and those edges will land up in the cut because we are making a greedy choice here. So size of cut is going to be sum over V in V. Again, for every vertex we are putting these RV by 2 many edges in the cut. So this is going to be RV by 2, which is sum of RV is mod E. So this is mod U. Just think about it for a while and ask me if something is not clear. And of course we can claim half approximation with this, since mod E is the size of the maximum. It's an upper bound of the maximum. So we have a deterministic algorithm which gives us a half approximation. For vertex cover we said that whatever we got, like 2 approximation, essentially the constant factor cannot be included under some conjectures that we believe. Here there is a much better algorithm than half, and you will see it maybe on 3rd or 4th day. Ramesh will cover it. And it is a much more sophisticated algorithm. You will see it later.
What's the constant there?
0.878, and it uses what is called as semi-definite programs. So what we have done today is only we designed combinatorial algorithms. We put this here, kind of. We did only combinatorial things, but one can use linear programs, semi-definite programs to design and analyze algorithms, and they give much better results, much better approximations possible sometimes compared to the straightforward combinatorial approaches. Yeah, so here for this particular problem you will see better approximation algorithm. And yeah, one contrast which I want to point out here. We saw the maximum cut problem. We said it is NP hard, and we designed half approximation. What about minimum cut?
All the vertices in one.
I believe there is a max flow min cut theorem which okay, I do not remember exactly what max flow was, but
Sure. Yeah.
it's like we can find the optimal answer using that.
Yes. Now, as someone pointed here, why not put all the vertices into one part and get a cut of 0 size? So that is something we want to prohibit. For maximum cut, it was automatically prohibited because we wanted to maximize the number of edges cut, and 0 is not a maximum. There is one more.
What if we take the complement of the graph and solve the max cut on it?
First of all, max cut is hard, whereas minimum cut is actually polynomial time. So, if at all we should do the other way around, find a minimum cut and take the complement. But even you can construct examples where that will not be the best thing to do.
Ma'am, if we take the vertex with the minimum degree and include it in one set and the other vertices in another set, then it will exclude the minimum number of edges from the.
For minimum cut?
Yeah.
No, again, so I think you can construct examples where there will be simpler things to do. Okay, I can also give an example here. So, suppose you have a graph with high degree here, and then there is an edge like this. So, the smallest cut is of size only 1. But if you take a minimum degree vertex, the degrees are pretty large.
No, I am just saying that I will take the minimum degree vertex and keep it in one, suppose set A and other vertices in set B. And then the resultant.
So here if you do that, you will get a cut of size 3, right?
No. Okay.
But there is a cut of size 1 as well.
Okay.
And this 3 you can increase n over 2 vertices here, n over 2 here. So minimum cut is polytime solvable. One can use max flows, for example. But it is important to keep this contrast in mind.
I might have missed something, but for example, for vertex V1 it has gone to set A. For vertex V2 it has gone to set B. Now for the vertex V3, since we haven't seen all the neighbors of V3 and only 2 neighbors we have seen, so what will be in that case the criteria? For example, the algorithm we simply think that it has more neighbors in A, we are going to put it on B and all.
So what kind of neighbors does VI have? It has some neighbors in A, some neighbors in B, and some are not yet classified. Forget about the unclassified neighbors. Only look at the neighbors it has in the number of neighbors it has in A versus the number of neighbors it has in B.
But if they are equal, then we are going to put it in.
Yeah, it can go to A.
But the criteria for putting it in A, like directly we are putting it on A, can we also have some kind of criteria like in which set we should hello? Like in future, if we put it in B, we might get a better set or not, better cut set or not.
So clearly we may not end up in an optimal solution, right? There will be possibly a bigger cut by doing something better. But what we are doing here is we are making a decision for VI, only looking at its already classified neighbors.
Okay.
And what we are saying here is that VI decides the fate of only those edges which have their other endpoint already classified. right? So whether vi goes here or here, only the fate of these edges and these edges gets decided.
So the order in which we are gonna put the vertices in those set also matters at the
Different orderings can give different outcomes,
Yeah.
yes. But here we are saying that no matter what ordering you use, you are guaranteed to get a half approximation.
Okay. Thank you.
I have a question on like when or how do you judge that greedy algorithm is better way to give an approximation schemes? Because previously mentioned for vertex cover, greedy approximation is not good, but for max cut, you're saying greedy. So how do you judge and like how do you get that intuition?
At least I don't get the intuition. So whenever I get a new problem, I would, of course, the greedy approach will be the first one to try out. So what I would do is try to construct counter examples which will beat the greedy approach or which will be bad for the greedy approach. So for vertex cover also, the problem set asks you to design examples where the approximation is much worse. It can be as bad as lock-in, as you will see in the problem set. So come up with examples where the greedy algorithm is performing very badly. So this coming up with examples takes a bit of practice, and it will come as you spend more and more time, solve more and more problems. But typically the first thing for greedy is to see if you can get a bad example, which tells you that greedy doesn't work. If you don't get a bad example, then it gives you a way of proving things. So here, if I try to show a bad example for greedy, I will this intuition will sort of fall through that, okay, every time we are including at least half the edges for which the vertex is responsible. Okay, so when you try to construct counter example for greedy, you will either get the counter example and it will force you to take a different approach, or it will give you the intuition to prove the correctness or right approximation factor for the greedy approach. Even like the field of approximation algorithms has developed over several years. So not that people came up with the best approximation right in the beginning. Someone developed some approximation, and people improved, someone else improved further. Some people showed inapproximability and so on. You may not do the best right at the beginning when you start with the problem, but eventually you will do more and more sophisticated things and try to improve.
More questions, comments?
Yes, so I am done, and as far as I am concerned, we will meet tomorrow.
Okay, so let's thank Rajatha. led to further strengthen your understanding of approximation algorithms with more interesting problems. So I would like to invite Ms. Rachna Hussain. So Rachna is a PhD student here at IISc. So she did a master's from JNU, and her research areas include algorithms, computational geometry, and discrete geometry. So yeah, please Rachna.
Thanks, Parag. Thanks for the introduction. Is mic working? And I'm audible at the back. Yeah, so in this lecture, we will be looking at another NP hard problem, which is the traveling salesman problem. And we look at some inapproximability result for the general TSP, and then look at variants of the TSP for which we can design qualifying approximation algorithms. So that would be the plan. So what is the problem setup here? Say we are given a bunch of cities, a finite number of cities, and between every pair of cities there is a cost associated if you want to travel from one city to the other city. Okay? And then the goal is you want to visit every city exactly once, come back to the starting city, and minimize the cost of travel. Right? So we can state it using graphs. And before that, let me introduce another problem, which is a special case of TSP in some sense, and that's the Hamiltonian cycle problem. So what is a Hamiltonian cycle? Yeah, that it's a cycle that spans the vertices of the graph. Right? So given a graph, G equal to V comma E, a Hamiltonian cycle is a spanning cycle. And this problem is known to be NP hard. And a decision version of this problem would be that given this Ham cycle instance, the graph, you want to know whether there exists a Hamiltonian cycle or not. A cycle that visits every vertex. Now coming to the TSP problem, let's define it with respect to graph. As an input, we now have a complete graph, because for every pair of vertices, for every pair of cities, we know what is the cost of traveling from one city to the other. So as an input, we have a complete graph. And we are also given a cost function. A cost which assigns a non-negative weight to every edge. And we are assuming that this, the problem is symmetric in the sense that the cost of traveling from x to y is same as coming from y to x. Okay? And then the goal is, so in terms of Hamiltonian cycle, how can we mention the goal here in the TSP problem? Find the minimum cost Ham cycle. Okay, so how can we solve this problem, the TSP problem? Like some brute force way of solving this problem? Yeah. So every cycle is essentially a permutation of the vertices, right? And because this graph is a complete graph, every possible permutation gives you a cycle entry. So you can iterate over these markers. I have to check which ones. Yeah. So some of the brute force way of solving this problem would be that you look at all possible n factorial these permutations and evaluate them and report the min cost cycle. And what would be the running time? Just roughly n to the n. Okay? Too bad. Can we do better than this? And we want to get an exact solution. And so how do we do that? Using DP? Yes, one approach is via DP. Until date, that is the best, the one that gives the exact solution, and so DP based solution. How do you do that? Just give some thought to it. It's not very trivial, but not very non-trivial either. It's known from early 1960s. How would you design a DP solution for TSP?
We try to expand over this set.
Expand on
We
the
start with, let's say, 2 vertices.
Right.
And then we expand to 3 vertices and try to encompass the whole.
Exactly. Right? You look at a subset of vertices, try to find an optimal tour there, not an optimal tour, rather an optimal path in that set, and then expand on it. Right? So I'll not give you the details of this, but the running time here turns out to be order something like 2 to the n. Okay, and this was known from early 60s. Now, can we do better than this? Or so far we have not been able to. And so people started looking at the approximate solutions for TSP. But then the first thing is, this is NP hard, that is there. So TSP is an NP hard problem. But there is more than this. There is a very strong negative result around it. And that is, you cannot get any alpha approximation algorithm for TSP assuming that P is not equal to A for any alpha. Please let me write that and we'll prove that as well. So here is the claim, a theorem rather, in approximability of TSP. And this alpha, in the proof I'll just assume that alpha is some constant, but this alpha is any, okay. There are so many things, and I hope this could be better. Okay. Okay, I'll try. Yeah, so this alpha can be, it's a function that can be computed in polynomial time. So some polytime computable function. Is it too small, the font size? Not readable? Okay. Yeah, so think of this alpha as some constant. Now we want to prove that we cannot design an alpha factor approximation algorithm for TSP. So how do we go about proving this result? Suppose we have already seen that Ham cycle, this finding or deciding whether a graph is Hamiltonian or not, that is an NP complete problem. Can you think of a reduction from this problem to TSP? In fact, that is the reduction we are going to look at. We'll assume that there is an alpha factor approximation algorithm for TSP, and that would imply that we can get a polytime algorithm for deciding this Ham cycle problem. Okay? So assuming, suppose A is an alpha factor polytime. Okay, and then we will show that this implies the decidability of, I'll call this ham cycle problem as abbreviated as ham. So how do we do this, like show this reduction? In general, how do we prove a reduction, a volatile reduction?
You create a new function that involves the old algorithm as subroutine.
Okay. See, you are given an instance of a Hamiltonian, you are given a graph. Okay. And from that graph, I want to get a complete graph. I want to get an instance for TSP. Right? So I have a graph. Let's say G is an input instance for this ham cycle problem. And then what do we do? This graph need not be a complete graph. Right? So from here, if
we'll show that if we can find an alpha across polytime algorithm for the TSP problem, then that means that we can find a Hamiltonian cycle.
Exactly, that is what we are going to do in the reduction. But then before that, we have to define the instance for TSP. So how do we define that instance? So as he suggested, right? In this new instance, if I can find a TSP tore of cost at most alpha times the optimal TSP tore, then I should be able to say that in the original graph G there is a ham cycle. Right? So does that suggest how should we define this, the instance for TSP? Is this font size fine now? Okay. So it's going to be a complete graph. I need to define the cost function, right? And the way we are going to do is this. So you take every edge, every pair of vertices, right? And if this edge happens to be in the graph G, then we assign a cost of 1 to this. And if otherwise, we'll set a cost to be some large value. In our case, we will set it to be alpha times n. Right? Now run this algorithm A on this graph G prime. Okay. So there are two cases. So if G has a ham cycle, now just write it. If this is a yes instance, then what can we say about the cost of TSP, optimal TSP? So G has a ham cycle, and for every edge in the graph G, the cost is equal to 1. So that ham cycle itself will be the optimal TSP tore. Okay, so if G has a ham cycle, then it implies that optimal TSP tore, OPT is equal to n. Right? And this algorithm, which is an alpha factor approximation algorithm, it will return me, so let A be the output of this, and this will give me an output whose cost is at most alpha times A. Right? The other case is G does not have a ham cycle. Then what would be the optimal cost of TSP? Like, can you lower bound it? It has to be more than alpha n. It has to include at least one edge which was not there in the original graph. Right? So the cost will be strictly more than alpha n. So OPT has to be more than alpha n, and this algorithm will return an answer which is more than alpha n. So you see the gap between the answer that we are getting in the yes instance for G and over here. So we can clearly distinguish whether, we can clearly know by looking at the output of this A whether the graph G has a hand cycle or not. Right? And what we assume that A is a polytime algorithm, and this mapping from G to G prime takes linear time, linear in the size of a graph. So what we have is that A is a polytime algorithm for the hand cycle problem, which violates the PNP thing. Okay? So this is not possible. This is a contradiction. Okay, I'll just stop here. So A is a polytime algo for deciding the hand cycle problem. Which we believe that P is not equal to N. So any question in the reduction, or so far like the problem definition, hand cycle, TSPs, is everything clear?
Could you give like an idea of why the ham cycle problem is NP-hard?
Okay. Yeah, again, you have to look at all the permutations, right? And the reduction, I think, is from Vertex cover, which is already known as a NP-hard problem. From there, you can reduce to the hand cycle problem, which will establish the hardness for this hand cycle.
I might have missed it. What is N exactly?
Did I not tell that? So we will be assuming that the size of vertex set is equal to N. Thank you for pointing that out.
So the Hamiltonian cycle, in the Hamiltonian cycle problem, is the problem is to find the cycle or saying whether the cycle exists or not?
As an optimization problem, you want to find the cycle. As a decision version of the problem, you just want to say whether the graph has a cycle or not, a spanning cycle.
So which problem is NP-hard? Is it
Both.
Both are NP-hard?
So we say decision version is NP complete.
Okay. Because I couldn't understand, because when you said the problem of the Hamiltonian cycle, you're saying about finding the cycle, but when you're proving, you're just looking at the decide.
Both are equivalent.
Thank you.
Okay, so here is a very strong negative result that says that TSP you cannot approximate to any alpha factor. So what do we do? And try to see, what change do we need to make in the proof so that this proof breaks. That is true. Alpha is some positive. To make this proof work, we had to assign this very, this large values to the edges which were not there in the graph, right? And suppose alpha is some large value, it means that this G prime, if you look at the edges of G prime, they are not following the triangle inequality. You know about the triangle inequality? Right? I have a triplet, say x, y, and z. There are some 3 vertices in my graph. And I want to maintain this, say, that the cost of going from x to z is always less than or equal to my plus the cost of going from y to z. Right? And the moment we impose this restriction on the cost function, we cannot assign such values to the edges in the graph, because so for example, I will have a triangle in my graph, it's a complete graph, and say these two edges have cost equal to 1, whereas to this edge I am assigning a cost of alpha n. So how much, maximum how much can I assign? 2, right? In order to, so that we don't violate the triangle inequality, right? So let's make that change and let's see what we get. So by the way, if my cost function, the input, I have a graph and I also have a cost function, if it satisfies the triangle inequality, then we say that we refer to the problem as a metric TSP problem. Anyone knows what a metric is? You have a set and you want to define some distance, notion of distance like between every pair, and that function, the function D, must satisfy certain conditions. So what are the conditions?
Non-negativity.
Non-negativity. Yeah. So distance between every pair must be non-negative. Second condition.
Homogeneity.
What is that?
If we take the metric is some, let's say function f, and if we take f of alpha x is equal to mod of
That
alpha.
is, no. So you're getting into the definition of norm. So one is non-negativity. The other is if it is equal to 0. Suppose distance between two vertices is equal to 0, then the vertices have to be the same vertices. Then there is symmetric condition which says that the distance from x to y is same as the distance from y to x. Now see that both these conditions are already being taken care of in the general TSP problem. We assume that the costs are non-negative and the symmetry is also there. Right? So if we enforce this third condition, which the triangle inequality, then we get that C is a metric on this graph. Okay. So in the metric TSP, I have my input is a complete graph. And C is a metric. Non-negativity, symmetry, and this triangle inequality is there. Okay. Now I'll show that this problem is also NP hard, but it is not, the condition is like, the situation is not as bad as here. So we'll first show that this metric, I'll not do the complete details here, like from here can you suggest a reduction from ham cycle to metric TSP?
You have all the edge weights as one.
Huh?
You have all the edge weights as one.
All the edge weights.
Is
So again we have the instance for this ham cycle, right? It need not be a complete graph. So first of all I want to define this. After this it is the same. I mean we should be able to distinguish between yes from the no instance. So we have to assign weights in a way that because it's a metric TSP, it must respect triangle inequality, and then the second condition, we should be able to distinguish between the yes and no instances. Okay, so how should we define the weights now? Okay, so G again, ham instance, and G prime yeah, it's 1 if E is in the graph G, and otherwise 2. So if all the edges have weights 1 or 2, then it's clear that the triangle inequality is satisfied, right? And how would we distinguish between yes and no? This yes thing remains the same. Op will be equal to n, and so here we will assume that there is a polytime algorithm for metric TSP. So that would return us a cost of n, whereas if it's a no instance, then it has to be more than n plus 1, right? N minus 1 edges with cost equal to 1, and there has to be at least one edge which has cost equal to 2. Okay? So do I need to write, or it's clear to all? Clear? Anyone has a question in the second reduction? So here we are not, here we are assuming that A has, this metric TSP has an polytime algorithm, and using that we want to arrive at the fact that if we have such an algorithm, then we should be able to decide between, we should be able to check whether the graph has a Hamilton cycle or not. Okay. Now on the lower bound side, there like the inapproximability for metric TSP, the best bound that is known so far is 123 over 122, and this was shown by Karpinski back in 2015. What does this mean? That we cannot get, we cannot design alpha factor algorithm for TSP, metric TSP, where the approximation ratio is anything better than that. And the conjectured bound is 4 over 3. People believe that, we should be able to improve it to 4 by 3. Okay, so given this thing, let's now try to design an approximation algorithm for metric TSP. So in the rest of the lecture, we will first see a simpler algorithm which has a 2 approximation, right? And then we will see what changes are needed to bring it down to 3 by 2, which is essentially the best known so far. There is an improvement, but the improvement is, I'll state that towards the end of the lecture. Any ideas? What can we do? See, we have a graph, a complete graph. Okay? Try to think of some other structure. You might have seen it in your data structures and algorithms course, which we can use to, we can, once we compute that, and then modify it to get a cycle, a spanning cycle. Okay.
And then we just go for a DFS, and then we make a Hamiltonian cycle.
Okay. Yeah, so exactly that's the algorithm. See, it's a complete graph, and complete graph, it's connected, and therefore we can get an MST. So you have a MST, let me call that as T, and then so So DFS essentially you want to, if you visit a node, you want to get back also, right? And for that, what we are going to do is we'll double the edges of this MST. Now once we double the edges, what is it that we get? The resulting graph. What is special about it? Every vertex will have, what would be the degree of every vertex? Even. And we know that a graph is Eulerian graph if and only if every vertex has an even degree. So you must be able to do an Euler tour of the graph. Okay. So we double the edges of T, and this gives us an Euler graph. So let's take an example and see it over there. Let's say I will just construct the MST. It's a complete graph. So I'll not draw all the edges. Let's say that's the minimum spanning tree, and we double the edges of this tree. So now every vertex has an even degree. So we can do an Euler tour of this graph, meaning that every edge we can traverse exactly once. Okay. So let's do an Euler tour. Say, let me number these vertices. So I'll just write the sequence of the vertices in which I'm not writing in terms of edges. I'm just writing the sequence of vertices in the order we are visiting them. Let's say we start with 1, we go to 2, then come back to 1, 3, go back to 1, 5, here we have to go to either 6 or 7. So say we go to 7, come back to 5, 6, 5, and finally 1. That's one possible Euler tour of this graph, right? And from here I want to get a TSP tour. I mean a cycle which will visit every vertex in the graph exactly once. So how do we do that? Just look at this sequence, what I can do in this sequence to get a permutation of these 7 vertices. What can I do? Whenever you see a vertex that has already been visited, strike it off. Okay. So I'm going to 1, 2, 3, 4, 5, 7, 6, and that's it. Okay. So the TSP tour I'm getting is 1, 2, 1 to 2, then 2 to 3, 3 to 4, 4 to 5, then to 7 to 6, and I will get back to the starting vertex. Okay. Right. So this will give us a TSP tour. Now what we want to show is that it is a 2 approximation algorithm. So how do we prove the 2 approx?
We have double edges, so
Yes.
we can say it's 2 times of MST.
Right. So initially I had a minimum spanning tree. Once I double the edges, the entire cost of this graph, just the MST with double the edges, will be 2 times the cost of T. The first thing is that. And when I am taking these shortcuts, so by the way this is called shortcutting. So it's essentially what it says is, say I have in my Euler tool, I have something like I'm going from x to y, then y to x, and then I'm going to z. We can get we can shortcut it and say that we can directly go from x to y to z. And the cost of this would be less than or equal to, so let's say this path is p prime, this is p. The cost of p prime would be less than equal to the cost of p. Now, why is this true? Because of triangle inequality. Okay. So now the proof is easy. The TSP that I am getting, I am denoting it as TSP. Let's say this is the cost of the tour that I am getting. It can be at most how much? 2 times the cost of the minimum spanning tree. So 2 times the cost of MST, and then so suppose I have an Euler tool, an optimal tool, and you remove one edge in this tool, what do you get? We get a path which is right, which is also a spanning tree, not just a tree. It is a spanning tree because it visits every vertex, and MST is the minimum spanning tree, right? So what we have is that the cost of MST will always be a lower bound for the cost of what? TSP, the optimal TSP tool. So this is at most 2 times the OPT. Very simple. So what is the key takeaway from this algorithm? Now we want to improve this 2 to 3 by 2. So where can we do some changes? You already know this? Okay, first let me ask the question that what is the main idea here, or what is the key takeaway from this algorithm? Okay. Okay. Okay.
We wanted an oil.
MST has? Fine, so?
We get MST in polytype and get approximation.
That is fine. I'm asking in terms of this algorithm. Now we want to change it and get a 3 by 2 approximation. So, see, here is the key observation. Suppose in my graph, I can get a subgraph. Suppose we can get a subgraph which satisfies the 2 properties. One is that it must be a spanning subgraph. It must visit every vertex in the graph. Span the vertices V of G. And second is that if we can ensure this graph is also Euler, okay, then what do we have is the cost of this subgraph. We call this subgraph as H. The cost of H and OPT, how are these two related? OPT has to be at most the cost of H. Okay, so once I get this such a subgraph in my graph, it's not exactly a subgraph, just think of it, some of the edges might be doubled, okay, but what we want is that every vertex must be there in this subgraph, plus every vertex must have even degree. Okay, so in order to this first condition will be taken care of if I get an MST for the graph. For the second condition, here what we did was we doubled every edge to make sure that every vertex has even degree. So what can we do now? What are the
Can we add the edges between the nodes having odd degrees?
yes. So first of all, how many odd degree vertices can be there? Huh? How n by 2?
Because the sum of
Can you quickly prove this?
the sum of all the degrees of a vertex is an even number.
Yes, the handshaking lemma in the graph. See, the sum of the degrees is twice the number of edges, which is an even number, and the sum of the degrees over all the vertices is split it into 2 sums. over even degree vertices and over odd degree vertices. So even degree sums up to even number. For odd degrees to sum up to even, we must have that the number of odd degree vertices is even. Right? So once I have this minimum spanning tree, so this T has even number of odd degree vertices. Right? And then one option is that you pair these vertices, right? And we will do it in an optimal way, meaning that we will look for minimum cost and optimal perfect matching, right? So everyone knows what a matching is. Matching is a collection of disjoint edges from the graph, okay? And perfect matching means that every vertex is there in the matching, and we are looking for one that has the minimum cost. Let me call this matching as M. So coming back to this example, let me redraw it. Let's say we get this. So, okay, here we have this 2, 3, 4, 5, 6, 7. These are odd degree vertices. Right? So we'll pair them up, and suppose this was the one which has the smallest cost. Okay? So the resulting graph that you are getting, it's a subgraph of the original graph, and every vertex now has even degree. And then we can do, once every vertex has even degree, this is an Euler graph. We can do an Euler tool and then do this shortcut to get the TSP tool. Is the algorithm clear?
Can you explain what the minimum cost perfect matching means?
Okay, so you know what a matching is? Okay. So suppose you have a graph. Okay, you have a graph. So a matching is a collection of disjoint edges. Collection of disjoint edges meaning no two edges must be sharing a vertex. Now, when I say perfect matching, so perfect matching is first of all possible if your graph has an even number of vertices. So here we have that these odd degree vertices are even in number. So now we want to pair up these vertices, we can pair them up. So when I have a matching, it is essentially a collection of edges. Every edge has a cost, sum of their cost, that will give me the cost of that matching. So for by minimum cost I mean one with the smallest cost. Okay? Any doubt? Is it clear?
For this minimum cost perfect matching part, is this computable in polynomial?
Yes. So usually that is not taught in the undergrad this data structures or algorithm course you do, but I think the best known is n to the 2.5, right? And I mean the Atman's algorithm, I guess it gives n cube runtime, but that is also not trivial either. Uses LP duality. I mean you have to formulate the problem as an LP, then look at its dual, and then do some other work to get the minimum cost perfect matching. So now the only thing that remains to be proven is that the TSP that we will get after doing an Euler tour here and then shortcutting, the TSP that we get has a cost at most 3/2 of the OPT. Okay. So let's prove that. So first of all, it will be at most the cost of the graph that I obtained, and the cost of this graph is the cost of the T that we got, the minimum spanning tree, plus the perfect matching that we have here. So it will be the cost of T plus the cost of M. Okay, and we already know this cost of T is, this is less than or equal to OPT. Now, if we can show this matching is at most half times the OPT, then we'll be done. So how do we prove this? The other part.
Take an Hamiltonian cycle. We take alternate edges, forms the matching.
Okay.
And this is a minimal matching in a subgraph of a complete graph.
Anyone who has not seen this can answer this? See, first of all, we are not obtaining this perfect matching on the entire set of vertices. We are only looking at the odd degree vertices in the resulting this MST. Okay, so you have to be very clear in your arguments when saying that the matching would be at most half times the OBD. Suppose you have an optimal tour in your graph. Okay, you have an optimal tour, say it's a cycle spanning every vertex, and then you build a TSP on this, right? And for that TSP, some of the vertices are odd. Okay, so let's say that these 3 vertices are, say these 4 vertices are the odd vertices. 3 cannot be. It has to be an even number. Right? So what I can do is, I can take a shortcut tour which only visits these black vertices. These are odd degree vertices in the minimum spanning tree. Right? If I take this shortcut, I get a cycle which spans only these vertices. Right? And because of, again, by the triangle inequality, the cost of this black cycle is at most the cost of the red cycle. The red one has, spanning the entire set of vertices. The black is only spanning the odd degree vertices in my minimum spanning tree, and by triangle inequality, so let's say this cost is, this path is P, so the cost of P will be less than or equal to the optimal TSP cost. Now, as she has suggested, I mean, I would like someone else to answer this. So what do we do now? With this black cycle, which is an even cycle, what can we say?
You can get a matching for this.
Yes. Yeah, by taking alternate edges, we get actually 2 matchings, and the cheaper of the 2 matchings will have cost how much? So the cost of M is the minimum cost perfect matching. This has to be less than or equal to the minimum of, so I'm calling, so let's say these 2 form the matching M1 and these 2 form the matching M2, then the minimum cost perfect matching over these vertices, which can include edges from the original graph, right? That has to be less than or equal to the cost of M1 and the cost of M2. Okay, and then simple, the cost of M1 plus cost of M2 by 2. And what is the numerator here? It's the cost of this entire cycle, the black cycle. Okay, because every edge is counted exactly once in the 2 sums. So what we get is the cost of, calling it as P by 2, and this is at most the optimal cost. And this establishes this 3 by 2 approximation factor. So this was the algorithm by Christophites, this 3/2 approximation, also known as the Christophites algorithm. Later, after 2 years, there was another person who also gave this 3/2 approximation algorithm, but he was the first one who gave this. It was in 76. And very recently, in 21, and for all that period, it remained a big open question whether one can improve the 3/2 factor. And then, the 21 is improved. Can anyone guess what the improved factor is? Yeah, it's 10 to the minus 36. Okay, and this was, I think, a stock 21 or Fox 21, but it received the best paper award. The algorithm is quite involved, and for a long time, I think the journal version was not there. By search for it, it's Carlin, Crane, and Carlin et al. They obtained this 3/2 minus 10 to the minus 36 approximation for this metric TSP. That is it. I mean, are there any questions? So there are other variants of TSPs as well. So this is symmetric TSP. There is also a version which is asymmetric TSP. Asymmetric. And here what we have is a directed graph. Right? So x to y and y to x, the cost may be different. So this problem, I think for the upper bound side, there is a log n approximation. It was known from 80s, I guess, which was later improved to log n by log n. And then the state of the art is there is a 22 approximation for this. And the inapproximability bound here is (75/74). Again, in the same paper, this Karpinski. I mean, no, this factor is possible. Conjecture to be conjectured lower bound here is 2. Okay, so that's it. If there are any questions then?
And there are also heuristic methods to solve or approximate TSP. So, do they provide any computational advantage or better approximation bounds? Like I recently came across ant colony optimization to approximate TSP. So, do you have any information about that?
No, I know that they are practically they are faster, but the bounds that we can prove theoretically, these are, for those we cannot really prove these better bounds.
Hi,
Hi, can you, so do you know what kind of ideas are used for that 123 by 2122?
This one, again they use, I mean I have not read it, so but the reduction is from some 3 regular CSPs to metric TSP. Yeah.
And why is the conjecture believed to be 4 by 3? Is the reason?
Okay, some LP relaxation, LP integrality gap.
Oh, okay.
So for for metric TSP it is 4 by 3 and for A TSP it is conjectured to be 2.
What about this one? 10 power minus 36. What are they doing actually?
I
Some
don't know.
theoretical methods or something. No.
No, I really haven't looked into that paper. Oh, yeah, there is a question.
So in the last algorithm, you said that after including the mean cost pattern matching edges,
Yes.
the odd degree vertex become even degree.
Hmm.
Can you explain why is that?
Okay. So, so suppose you have a tree, okay, and there are even number of say 4 odd degree vertices. So what you will do is you will pair 2 of them and pair the remaining 2. So now all 4 of this, their degrees get added by 1, right? Earlier it was odd degree. Now it is +1, which is even.
Okay, let's say one of the perfect matching edges is already there in.
Oh, so there you will add an edge. So you will double the edge. That is why I said when I was mentioning this subgraph thing, some edges are doubled. The example that I gave, there I actually took those edges, the perfect matching edges were different from the TSP, the MST edges, but you can have, in that case you will have to add a double edge.
So in TSP, usually the input is complete graph is what we say.
Yeah.
So what if we are given a graph which is not complete? Like, can we convert it to a complete graph?
Yeah. To add edges.
But the weights.
With all the weights greater than the weights we already have.
Without, sorry?
So the weights that we add to make it complete, we can give the weights greater than what we already have. So in the end, if the minimum path, what we want, that has edges with weights that we have added later on, that means there wasn't one previously.
And you can fix some maximum, which is the sum of the weights of all the edges, and assign that to the remaining missing edges in your graph. Yeah, and one more thing I forgot to mention, this metric, a special metric is the Euclidean metric. And I mean there, the cost between, so every point is in the plane, and the cost between the 2 points is the distance between those 2 points, the Euclidean distance between those points. So that is Euclidean TSP. So a Euclidean space, I mean it's an example of a metric space. So for Euclidean TSP, 1 plus epsilon is known, 1 plus epsilon approximation is known, and that was one of the big results. So Sanjay Arora and later Joseph Michel, they came up with the pitas for Euclidean TSP, and both of them received Gödel Prize in 2010, which is one of the most
instant.
So they gave pitas for Euclidean TSP. So that is worth looking at. It's there in the textbooks, the standard textbooks for approximation algorithms by David Williamson and the other by Vasirani. You can take a look at the Euclidean TSP algorithm. Okay, so thank you all for attending.
Rachna for this amazing session. So on behalf of the summer school team, I'd like to present you this case.
Thank you.
Yeah, so next we would have lunch and we'll meet again at 2:15. So the next session will be from Professor Nita.
For the just instance again, I will have a optimal tool of size n, and then approximation algorithm that will return me the cost of the